Hello and welcome to our KEB web seminar, The Digital Twin. My name is Tobias Wenneker and I'm working in the product management for our KEB industrial drives. Since 2004 I'm working at KEB in Bahntrup. I'm starting my career in service, where I worked as a service consultant for commissioning, troubleshooting and trainings. Since 2004 I'm working as a product manager for our KEB industrial drives. Now I hand over to my colleague Manuel.
Yeah, thank you. Hello and good afternoon, ladies and gentlemen. I am Manuel Brose and I work at KEB Automation since 2017. I have studied electrical engineering and mechatronic systems at the University for Applied Sciences and Arts in Lemgo, Ostwestfalen-Lippe. And even during my study work, I also got some insights at the topic real-time simulation of power electronics. And after a short time as a scientific researcher at the Institute Future Energy, I got to KEB, where I am now working at the fundamental development and research department. And my basic topic is to develop and work on our drive controller on our simulation models of our drive controllers, with the focus on the simulative behavior of our drive controller firmware.
Okay, many thanks to you, Manuel.
Yeah, thank you.
Now I'd like to give you an overview about today's topics. The first topic block will be done by myself, and I'd like to give you an introduction about the broad topic of the digital twin, related interpretations, concepts, products and application areas of KEB simulation modules. The second topic block will be done by Manuel. He likes to give you an history feedback about the success story of KEB drive controller firmware simulation modules, considered simulation environments, application for virtual commissioning, and a small report from the research project ITS-OWL TEDZ of Technology Network ITS-OWL. And at the end, we'd like to give you a short conclusion about the web seminar. KEB Automation. Who we are. KEB Automation is an independent, family-owned, medium-sized company. All around the world we have got 5 production plants, and we have got a broad portfolio for automation solutions like brakes, motors and gears, of course drives and controllers, HMIs, software solutions for remote maintenance, and a scalable digital ecosystem, KEB NOAA. KEB is characterized by a high vertical range of manufacture here in Bahntrup and also at the other plants. We work together in a close relationship with our customers and machine builders, and we have got a lot of innovations in the background and in our product to be state-of-the-art in the market. The term digital twin. Yeah, the digital twin is always in a context over the old topic Industry 4.0 and promises crossover manufacture exchange of standardized data such as communication, service and semantics. Personally, I think the digital twin is a great opportunity, a component of the digital transformation in the future and now, to make the automation industry and other technical areas as well as product developments smarter and more efficient. Join us at this exciting path. Now I like to give you an overview about the possible submodels of the asset administration shell. The Industry 4.0 platform shows that the digital twin is already named in the asset administration shell. It could be, in addition to the possibilities of the showed industrial administration shell, that submodels in the future can be added with further values like contact informations or contact persons. KEB is currently actively involved in the Industrial Digital Twin Association Committee. We are working extremely in the submodel simulation, such as drive controller software. The next slide is about the product itself, the physical asset, and on the right side, the digital twin. The F6 and S6 multipurpose drive series is characterized by the functional consistency and high scalability. Also, a compact design, especially in the medium and large power range, is given by the physical asset and our current product. The current product, S6 and F6, has got a volume from the 750 watt up to 450 kilowatt. Also, inside the software functionality, we can run different motor types like asynchronous motors, synchronous reluctance motors, linear, high speed and high torque motors. Of course, we can run our own motors, and as well we can run third-party motors. Also, we can run different encoders, for example HDL, Syncos encoders, other digital encoders like NDAT and so on. Also, the communication over the field bus system is given with our drive controller S6 and F6. For example, we can run the communication part with EtherCAT, Profinet, Ethernet IP, Modbus TCP, PowerLink, Varan, and the classical one, the CAN. Also, the drive controller can be used with a wide range of controllers in this case. And now we like to shift from the physical asset to the digital twin. The attributes of the digital twin in the field of drive controllers. They are flexible because the digital twin can be used for all applications. They are compact because often the digital twin sub information can be handed over to our customers as a user package. And the reliable is given because the digital twin is tested by ourselves and they are certified by the producers, in example ourselves, and as well as from independent bodies, for example product data tests. The performance shows with a simulation depth can be scaled by the user, and the simulation environment can be selected according to the requirements from the customers and the machine builders. Also, like the physical asset, the digital twin is communicative. What does it mean? Of course, we are planning, or we developed that the digital twin can communicate like a standard or an usual drive controller with the simulation model over the field bus communications, for example, EtherCAT or Profinet. In fact, it means that you have no difference to the real drive. And last item about the scalability of the digital twin is a precise topic, because the reproducibility of application behavior as well as configuration can be investigated and improved during the development process. The next slide is about applications and applications examples and one use case from the digital twin and our product F6. The first information you see in this slide are the different applications KEB work on currently and of course in the past. For example, plastic machines like extruders, injection molding machines, woodworking machines, especially spindles for the application milling, sawing and drilling, CNC applications, and also the metal working in this area, the passenger elevators, intralogistics like cranes, construction cranes and many more. Textile machines are also in the range of our application, for example the ring spindles and the waving machines. Compressors and packaging machines round the applications up in the industrial area. Of course, we have got some applications at test benches and many more. The example from a use case from the digital twin and a physical asset was done with a customer for a woodworking machine. The requirements and ideas and wishes for a drive controller and the drive controller digital twin were developed together with our customers. The use case for the woodworking machine is for the high-speed motor spindle, to run this high-speed motor spindle sensorless with communication protocol Ethernet EtherCAT, I'm sorry. And last but not least, we have got, in case of this use case, a multi-access application. And the most important point for this project or the use case is that we hand over all information as a package to our customers. Installation manuals, programming manuals, volumes of the sizes of the KEB drive controller and the drive firmware simulation model. The use case is not an Industry 4.0 illusion, it's a realistic use case at and with our customers from KEB. Now I hand over to my colleague Manuel to give you further information about KEB and firmware simulation models at KEB.
Thank you, Tobias. I want to give you for now a short overview about the term firmware simulation models at KEB. So we'll start with this. I will give you a little bit of a short review how we even started to use the term firmware simulation models. So there was a customer request in 2017 for simulation models of our older generation, the F5 drive controllers for the simulation tool ISG Virtuos. At this point, at this time, our focus was mainly on the hardware in the loop simulation, the HIL simulations. So for this, the models of the drive controller software were not considered back then, even at KEB. So at first I had to learn a little bit more about the environment TwinCAT, which is a real-time environment on a Windows-based system with connection to a real-time Ethernet like EtherCAT, and the environment ISG Virtuos, which is a simulation tool to model the system or the plant, for example, to simulate a conveyor belt system. So how does the model look like? At ISG Virtuos, it is possible to implement C++ user code models. But for our F5 drive controller, we couldn't implement our assembler firmware code. So we had to do some re-engineering to model the behavior of our F5 drive controller for a certain range and for some certain functionalities. So the modeling was done by standard model blocks from the library of ISG Virtuos and a C++ model to handle the set programmable parameters of the F5. Furthermore, the mode positioning was implemented. So there are some certain disadvantages for this approach. There's like a limited maintainability because these models tend to get more and more complex after time. There's a very high effort to integrate new functions, and that's like the very most important part. We cannot transfer the model directly to further simulation tools, for example, MATLAB Simulink. But we could overcome this by using the firmware of our newest drive controller generation, the 6th generation, in simulation models. So we started to develop our firmware-based simulation models of our F6 and S6 drive controllers in 2019. With this approach, by using the firmware, the current firmware in our simulation models, we have several advantages in comparison to the old F5 simulation models, like a very high representation of the real behavior because the original firmware is used. There will be many drive controller specific functionalities will be covered directly. We also considered scalable levels of detail for different fields of simulation applications. For example, there might be some motor models in simulation tools who cannot be modeled, so they have to be idealized, for example. Furthermore, the firmware simulation models are generally integrable in simulation tools with user code-based model blocks. There's also very low maintenance because all drive controllers have specific or do have directly the specific functions already in the firmware. And one of our very important concerns is the intellectual property, the IP. But this is nowadays given by most of the simulation tools because the models will be pre-compiled handed over to the customer. So IP protection is a very important point, and it is covered by most of the simulation tools nowadays. So these current firmware simulation models are mainly developed for actually two simulation environments at the moment. On the left side, we see the Scalexio real-time system from DSpace, which is a modular real-time system with scalable I/O requirements. It has a connection to the real-time Ethernet EtherCAT, and the modeling tool for the simulation models is MATLAB Simulink. On the right side, we have TwinCAT and ISG Virtuos real-time system, which is a Windows-based real-time system. It also has a connection to the real-time Ethernet, the EtherCAT, amongst others, and the modeling tool for the simulation tools, for the simulation models, is ISG Virtuos. So with these two environments, we face different simulation applications. On the left side, for the Scalexio system from DSpace, we have the ability to have, that we can go down with a level of detail down to the power modules of our drive controllers, for example, to investigate the control behavior. We also have the ability to be on simulation step sizes in the range of our basic control grid of our drive controller. So with the DSpace Scalexio system, we can consider very high detailed models overall. On the right side, for the TwinCAT and ISG Virtuos system, the level of detail is mainly at a functional level of a machine and a plant. For example, to only validate the functions of the engineered PLC code. Because of that, the power module and the motors are mostly very ideal models. So after a short comparison, we will go over to a use case and take a look at that. So the use case is called the virtual commissioning. For this use case, we assume an exemplary machine which has to be developed at one of our customers. The system is connected to a PLC with a real-time Ethernet, just like EtherCAT. There are some access also in this application and a woodworking application. So all of these components are transferred as simulation models to a real-time system, which is also connected to the original PLC, just like in the original application. The real-time system has also control and display elements, as well as 3D visualizations to show the current states of the woodworking application. Specific errors can be integrated into the real-time system to test the behavior of the PLC in a realistic situation. Initial configuration of the system can also be tested. So with this setup, tests of first functionalities are done virtually before the real commissioning. Some possible examples to detect some errors of the PLC code are, for example, faulty configurations of the PDO mapping, incorrect configuration of the digital input functions, and also handling of error scenarios with drive-specific errors. For example, we assume a reduced DC link voltage and the PLC code has to ramp down the system. So this is only one use case. In another use case, we enhanced this use case virtual commissioning with high detailed models. This was done in a research project called ITSOVL TDZ. There we considered a conveyor belt system with 3 conveyor belts and a vertical lifting axis. The purpose of this system is to move the material from the upper left position to the lower right position along the depicted motion trajectory and backwards. The system was designated to be operated by KEB C6 E22 PLC with a real-time Ethernet EtherCAT. For this use case, we chose the DSpace Scalexio real-time system because of the ability for integrating very high detailed models. So the conveyor belt system was modeled in MATLAB Simulink and transferred with the DSpace toolchain onto this Galaxy real-time system. After developing and transferring the models to this Galaxy system, we achieved, just at the very first moment, very good results at the first time plugging in our PLC with the not modified PLC code. So with this project and research work, we closed the gap a little bit more to enhance conventional virtual commissioning with high detailed simulation models, including the firmware simulation models.
Well done. Okay, Manuel, many thanks for this detailed information about the current situation for our firmware simulation models at KEB. Now we'd like to give you a conclusion about this digital twin web seminar. The engineering will become smarter in the future. That means that through virtual commissioning and possible machine scenarios in the future and simulation environment, you will become much more smarter and efficient. The on-site commissioning can be made more efficient as well through the previously and virtual commissioning in front of machine engineering. And the employees and customer trainings can take place virtually and flexible according to the customer requirements and machine builder requirements. And the support can act in a more targeted manner in this case to achieve a more efficient service at the end.
Yeah, reproducible tests of application and configurations are of course possible to improve the development process at customers. We can also give a more accurate simulative support at engineering of machines and plants, for example, to be more resource efficient. Generally, custom applications determine the requirements of the simulation depth of a machine or a plant. With our firmware simulation models, we are looking into the direction of very high detailed as well as reduced detailed firmware simulation models.
Okay, many thanks for watching this KEB web seminar and keep in touch in the future.
Yeah, thank you.